In this example, we are asked to complete the table of differences, and we are asked, can this data be modeled by a linear function, why or why not? So we have to think about what we know, and the key thing that we know is that linear has constant change. So let's take a look at our data. We are looking at a credit card debt. The card was used for a $395 purchase, and no payments have been made, right? So we're to use X for months since the purchase, and we're to use Y for the balance of the credit card. So our X value we see here every 3 months, we're given an input, and our balance is that input. So change in Y, we know that that is where we subtract. So we take Y2 minus Y1. Y2 is our second value. So I'll write this all out for the first one, 409.39. And then we're going to subtract 395. And so when I do that math, I get 14.39. And so then I do the next one. And so this one, I'll start at the 6 here. So 424.31 is the balance of 6 months minus the 409.39. And when I do that, I get 14.92. So a little bit higher jump there over those 3 months. And so immediately these two numbers don't match. So can it be modeled by a linear function? No. Why not? The change is not constant. So I'll just complete the table here to finish the work. So I'll take the value or the balance at 9 months, the 439.77 minus the 424.31, and I'll get 15.49. So again, this was a bigger change and not a constant change, so 15.46. And I'll subtract one more time the 12-month balance minus the 9-month balance, and for that, I get 16.12. So those confirm that the change is distinctively not constant. So the next it asks me, can this data be modeled by an exponential function? Well, what do I know about exponential? Exponential has to have a constant y ratio. So I'm going to take a look at the y ratios, and I'm told here to put y2 over y1. So for this first one, 409.39 divided by the y1 value of 395. And I get, and I'm going to keep a bunch of decimals so that we can see these truly are the same, 1.0364. 1.0364. All right, so then I try it again using the next pair of numbers. So my y2 is 424.31 divided by a y1 of 409.39. And I divide that out, and I get a matching y ratio. So I'm leaning towards that this is indeed exponential. But I'll double check. So I'll do these last two. So this is 9 to 6, so I would take the 439.77, divide by the 424.31, and I get the exact same ratio. And if I divide the last two, y2 over y1, I once again get the exact same ratio. So can it be modeled by an exponential function? Yes, it absolutely can. And why can it be modeled is because it has a constant ratio. A constant ratio indicates that it is changing by a percentage. And so in this case, the percentage probably the interest that the credit card is charging is constant. And so indicates a constant percentage. We are going to learn a lot more about exponential in the upcoming weeks. But for right now, we can write a formula even though they didn't ask us to. So from last week, we learned that you can use the impact model to create a formula for exponential, and we learned that the P is the start. We learned that the A is the ratio, and T is the time. Now, this one is a little bit more involved than any of the ones we've previously seen, and that is because our time did not go up by a single time a month. It went up by 3 months. So we will still start with the starting amount. So that was the purchase of $395. We will put in the ratio, so 1.0364. And then because the time went up by 3, my exponent is going to have to be t divided by 3. And we will get into why that is, but t is where the time is, and it is the time that's going up by 3. So that is why the time has to be divided by 3. So if I think this through, like for 6 months, if I look at this, well, how much did the balance go up? Well, it went up twice. So if I take 6 and plug it in for the time, 6 divided by 3 would give me a 2. And so that's because the balance has gone up 2 times in my chart. And so that's why we use that fractional exponent. But as I said, we will circle back to that as we learn more about exponential functions. Key for this week is that this is distinctively not linear